This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, the professor for this class, and this is our second lecture on lithography, where we give a process overview. Our reading is Chapter 7 again from our textbook by Campbell. As we saw last time, the basic lithography sequence was carried out on a track connected to a stepper or scanner in a system combined that we call a photocell. And a wafer comes in, it gets coated with photoresist, it gets baked, it gets exposed on our scanner, which projects an image of the photomask onto the wafer. The exposed wafer is then baked again and developed before being measured and moving on to subsequent process steps. We're going to look at these steps in a bit more detail today. But before we do that, let's look at the process requirements for lithography. The first requirement is maybe the most obvious one. We're trying to form an image of the mask onto the wafer. So the first requirement is that we have some faithful reproduction of the patterns that we're trying to print. That means quite a few different things, but most importantly it means getting the right dimensions of the features that we're trying to print. The dimensions of importance we call the critical dimensions. Nowadays there's virtually nothing that's not important, but nonetheless we tend to call the dimensions that we might measure or keep track of the critical dimensions, and we use the abbreviation CD very universally in the world of lithography. We talk about the CD. But once we form these patterns, we have to use them, and the way we use them is in a pattern transfer process. Mostly they're used for etch. So the photoresist becomes a mask for the etch pattern transfer process. So we need good etch resistance. We need a photoresist that etches very slowly in the chemistries that we want to use. We want good selectivity of the etching of the film compared to the photoresist. But we also want a resist that can stop ions when we use that photoresist as a mask for the ion implantation process. We call that the stopping power. How thick do we need the resist to be in order to stop the implant from going through the resist and into the substrate? This is a part of the pattern transfer characteristics of the photoresist that we require. The photoresist must stick to the substrate. I've seen plenty of beautiful resist patterns that were imaged on the wafer only to peel off during some subsequent processing because of lack of adhesion of the photoresist to the substrate, in which case all those beautiful patterns go to waste. Lithography is not done alone. It's done as part of the overall process of chip making, and we do lithography multiple times. Typical DRAM processes might require 25 lithography steps to make the chip. A typical microprocessor or logic process might require 50 or 60 lithography steps to make the chip. Every one of these patterns that we're printing on the wafer has to be aligned to the previous patterns that have already been printed on the wafer. And so the proper alignment to previous levels is just as critical as getting that particular pattern imaged faithfully. When we're done, especially when we're done with our etch and maybe our implant, we strip away the photoresist. It's kind of interesting that unlike deposition and etch and all of the other process steps we've talked about so far, the handiwork of the lithographer never gets shipped to a customer. When we're done with our lithography process, we strip the photoresist away. And finally, the standard things that are required of any manufacturing process. They must have low defects, they must be cost effective, safe, and environmentally responsible. So let's talk about the photoresist a moment, and then we'll talk about processing the photoresist. And today we're going to give a brief overview of the process steps, and we'll talk about some of these steps in much more detail later. The photoresist, which is a photographic photosensitive film, has two functions. A photoresist must photo and it must resist. What does that mean? Photo means form an image. We need to form the high resolution image faithfully, getting the right dimensions without defects and with enough pattern fidelity that we can say we've succeeded. But it also must resist. It must resist etching in order to transfer that pattern, and it must have stopping power to transfer the implant pattern into the underlying layers or wafer. To accomplish both of these tasks require some pretty sophisticated and specialized chemical formulations. We're going to go into the chemistry of photoresist later, but what we can ascertain as of right now, if it's sophisticated and specialized, you know it's expensive, and a bottle of photoresist is quite expensive. Think about a liter costing $1,000 to thousands of dollars for this photoresist material. So let's go through the process step. Our first thing we want to do is coat the wafer with our photoresist, but we can't just start doing that. We have to begin by preparing the substrate. The purpose of substrate preparation is to make sure the photoresist sticks. We have good adhesion. The first rule of adhesion: things don't stick to things that are dirty. So we begin by cleaning the wafer. And to clean it, we want to get rid of two things. We want to get rid of the particles that might be on the wafer, and we want to get rid of any contaminant films or materials that might be coated on there. Just like we've talked about in the past with particles, we want to eliminate the source, and then we do cleaning to eliminate whatever might still be on the wafer. But there's an interesting new contaminant that we worry about in photoresist coating, and that's water. Our photoresists tend to be hydrophobic. They don't like water. If there's water adhered to the surface of the wafer, then we will get poor adhesion of our hydrophobic photoresist when coating. So we spend some time thinking about how to get rid of the water, and we do it in two ways: by removing the water and then adding an adhesion promoter. The reason we have a problem with water has to do with the top surface. So you know the silicon is this matrix of tetrahedral crystal structures. I show it here in a flat two-dimensional array. Every silicon is bonded to four other silicon, except the top surface of the wafer. The top monolayer of silicon is not bound to four other silicons. It has an extra bond just hanging there waiting for another silicon to attach to it. What happens with these dangling bonds? Well, one thing can happen is water can adhere to the surface. The electrons of the oxygen like to supply the extra electron density that the silicon wants for this dangling bonds, and we get some nice adhesion of water, a monolayer of water on the surface. Now, we try to coat photoresist onto the wafer, and the resist is not coating on the silicon, it's coating on a layer of water. How do we get rid of this? We do it in two steps. First, a dehydration bake. We bake at a high temperature. If I did nothing but bake, it would take 300 to 400 degrees C to break those bonds and get the water off. But we don't want to bake at that high of a temperature, so instead we bake it closer to 100 degrees C in vacuum. We use a nitrogen purge, and these combination of steps tend to remove the water. You know, if we remove the water and then tried to coat, that would not be good enough, because we can't coat on a hot wafer. We have to let the wafer cool. If we let the wafer cool in an ambient environment, the water's just going to come right back. So we need to let it cool in a completely dry environment, and then coat really, really fast and hope no water gets on it by the time we coat it. Or we need to seal that top layer of silicon dangling bonds with something called an adhesion promoter. Adhesion promoter is simply a material that will react with those silicon dangling bonds in such a way that water will not come. The material we tend to use is hexamethyl disilazane, or HMDS. It's applied as a vapor, usually at the same time we dehydrate. We dehydrate, and then before the wafer even cools down, we throw in some HMDS. It's a vapor at 100 degrees C, and it just coats the wafer with a model layer of HMDS. Well, the difference is photoresist will adhere well to HMDS, even though it won't adhere well to water. This is usually performed in the same track system immediately before we coat. So the wafers come in, they go through this bake and adhesion promotion step, the wafer is cooled off, and then immediately is coated. Well, let's look at that coating step then. We've talked about deposition of materials and the many different ways we can deposit materials. We can grow an oxide, we can deposit through evaporation or sputtering, so-called physical vapor deposition. We can deposit with chemical vapor deposition. We can also spin coat a polymer. To do this, we begin by making our photoresist a liquid. We do that by dissolving it in a solvent. Then we pour the liquid onto the wafer. So the right half of this image shows just a puddle. Of course, really, it's a puddle on both halves. But we split the image to show you these two steps. In the first step, we pour a puddle of liquid photoresist on the wafer. It's reasonably high viscosity, anywhere from 20 to 10 to 30 or 40 centipoise. 1 centipoise, by the way, is the viscosity of water at room temperature. So 20 to 30 times as thick, more like the consistency of maple syrup. So we pour a big plop of this photoresist onto the wafer. The wafer is vacuum held onto a chuck that is on a spindle, and then we're going to spin it. We're going to spin it at, well, thousands of RPM. And as it spins, this puddle shoots off the wafer and off the sides. As it shoots off, it begins to evaporate solvent and solidify. At 1,000 RPM, that's a lot of airflow going on and very quick evaporation of solvent. The viscosity grows in this photoresist by 5 to 10 orders of magnitude during the spin coat process. It goes from a liquid to a solid. Once the viscosity becomes great enough, the fluid will no longer flow off of the sides of the wafer. When that happens, we've got a film of photoresist. We also have this thing called edge bead removal, which we'll talk about later, so I won't go over that right now. Then we have a couple of drains. Most of the photoresist goes down the drain. If we pour, say, 2 milliliters of photoresist on the wafer, a typical volume, maybe 90% of that resist goes down the drain, and the rest remains on the surface of the wafer when we're done. The goals of spin coating: to get the right thickness with good uniformity across the wafer. We want to be free of particles and pinholes, and we want a consistent lithographic response, which is really about getting consistent solvent content everywhere across the wafer. Once this spin coating also controls the final thickness, and this is a very simple and important relationship. The thickness of the resist coated onto the wafer is proportional to 1 over the square root of the spin speed. So this omega is the rotational spin speed, in RPM, for example, or some other units. And thickness is directly proportional to 1 over the square root of the spin speed. So how do I get a thinner coating? I spin it at a higher speed. If I want a thicker coating, I spin it at a lower speed. And I get this 1 over the square root of spin speed relationship. That gives me a fairly wide range of thicknesses available to me. But I can only spin so fast or so slow. So to get a wider range further, I can change the viscosity of the photoresist. So higher viscosity materials coat thicker, lower viscosity materials will coat more thin. Here I show a range of thicknesses that are over a micron thick, kind of older technology materials or materials used for ion implantation, for example. But we could also spin thinner and thinner and thinner using both higher spin speeds and lower viscosities. And today we commonly spin up films with thicknesses below 100 nanometers, even as low as 50 nanometers and below. There is another phenomenon that is important to mention here going on in this spin coating process, and that's called the edge bead. First, though, let's ask ourselves the question, how uniform can this film be? I mean, if you think about it, I'm pouring resist onto a wafer and then spinning it. Pretty simple, conceptually, a simple process. We take great care at the uniformity of the airflow and the temperature to get the best thickness uniformity of this spin-coated material, but the results are phenomenally good. I can take a 300 millimeter wafer, the biggest wafers we can coat, and spin coat a polymer film in 60 seconds and achieve a uniformity of thickness better than 1 nanometer. A few angstroms of uniformity across the wafer. It's really quite remarkable that this process can achieve that. Most of the other deposition processes we use in semiconductor manufacturing don't have nearly as good of uniformity. But there is one area of the wafer where we don't get good uniformity, and that's the edge. And the reason we don't is because of this phenomenon called the edge bead. What is an edge bead? Well, think about the process of spin coating where I'm pushing the solvent off the edge and a drop then flies off. As the evaporation occurs, the viscosity grows and it gets harder and harder for this film to fly off. In the middle of the wafer, most of the wafer, there's only 2 forces at work. There's the centripetal force trying to push it off the wafer and the viscous drag force trying to hold it back. Eventually those 2 forces become equal to each other and the fluid stops flowing. But on the edge of the wafer there is a 3rd force at work, and that's the surface tension. In the middle of the wafer, surface tension points up and down so it doesn't affect the flow, but at the edge of the wafer the surface tension, which is always perpendicular to the surface, is pointing in. So the surface tension is actually holding the resist back, and so it stops flowing sooner at the edge than in the bulk. The resist is flowing out towards the edge, but this extra force at the edge is holding it in place. The result is a bulge of photoresist called an edge bead. This is a nasty bit of resist on the edge. If we ever try to grab the wafer on the edges, we will get particles of resist flying off everywhere. It's very bad for contamination. So we end up removing this material with an edge bead removal. We do it right after we're done spin coating, so in the same tool. And generally we just spray some solvent at the bottom and at the top. We spray a little bit of solvent while we spin slowly, just enough to dissolve away the edge bead, but not so much that the solvent will affect the main part of the photoresist at all. When we're done coating, the film is not ready to go yet because there's still a lot of solvent remaining in the photoresist, and we need to evaporate that solvent to create a stable film. We do a post-apply bake. Immediately after coating, we put it on a hot plate that bakes the photoresist and removes residual solvent that's left after the spin coat. Even though we're doing this bake, we can still have quite a bit of solvent remaining after the post-apply bake, typically on the order of 5%, but for thicker resists it can be as high as 15% solvent remaining after the post-exposure bake. That's okay. The solvent is entrapped in that photoresist enough, held in place enough that it won't evaporate at room temperature after we've done this post-apply bake. This bake step is also called a soft bake or a pre-bake, but the most common name is the post-apply bake. Now we're going to go into our exposure tool. I'll only briefly talk about this exposure process today because we're going to talk a lot more about it later. We load a photomask or a reticle or just a mask, we use all these names, into the scanner, and it contains all of the patterns that we want to print onto the wafer. It's typically 4x, 4 times bigger than the pattern, so we're going to do a reduction image. The standard photomask size is square inch, a 6-inch square. It's made of fused silica, which we often call quartz, and it's about 1/4 of an inch thick, as you can see here. The patterns are made as opaque regions out of chrome, or sometimes molybdenum silicide, MOSI, we say, as the absorbing material. So we have a transparent quartz or fused silica and chrome or MOSI as the absorbing material for the 2 different transmittances of our mask. We make this mask in a lithographic process that is very interesting in and of itself, using electron beams to expose a resist, but we're not going to have the time to talk about that here. The patterns on the photomask are defined by the design of the chip that we're trying to make, and that design is then printed on the mask, and we'll use the mask to print on the wafers. The mask is loaded in our scanner, say up here, and then we shine light through the scanner, which then goes through a lens and exposes our wafer. Before we can do this exposure, the mask and the wafer have to be lined up properly. In an alignment step, we shine the light. The mask transmits in the clear regions and does not transmit or is absorbed in the opaque regions. We collect the transmitted light with our very, very expensive lens and project the image onto the wafer. Unfortunately, our lenses aren't big enough to expose the entire wafer all at once, and neither are our photomasks, and instead we only expose a small portion. And then we either step or scan the wafer to repeat this exposure over and over again until we fill up the whole wafer with our patterns. Once we're done exposing, we're going to develop. The wafer comes out of the scanner, goes back into the track. Sometimes we do a second, almost always we do a second bake step between exposure and development. We'll talk about that later. But then we develop. The developer is poured on or sprayed on to a slowly spinning wafer. If we have a positive resist, the developer removes the exposed parts of the photoresist. If we have a negative resist, the opposite happens. The developer removes the unexposed parts and the exposed parts remain. We call this the tone of the photoresist, a positive tone resist or a negative tone resist. And of course, we have to use different chemistry in the photoresist to make this a positive or a negative tone. We want our photoresist to be highly nonlinear in their response, and we call the nonlinearity the contrast of the photoresist. And we'll talk more about those subjects later as well. The result? Lots of different patterns printed in the photoresist. Our chip patterns, which could be over topography of other patterns existing on the wafer, and of course our goal usually is to make these patterns very small and well controlled and in the right spot. And we'll talk about all those subjects more in greater detail as we go on. Let's look at what we've learned. You should be able to quickly and easily answer these questions. If not, please go back and review the material from this lecture. How many, not may, how many requirements for lithography can you name? We went through quite a few of them. How many can you name? Hopefully most of them. What are the two main tasks of a photoresist? How does an adhesion promoter work? And why do we need it? What is the relationship between resist thickness and spin speed? What is an edge bead? Why does it occur? And what do we do about it? What is the purpose of a post-apply bake? And finally, explain the two tones of a photoresist. Of photoresists. Well, that's lecture 38, our second lecture on lithography. We have a lot of things yet to cover. Till then.